Welcome, everyone. Today, we are diving into the geological timescale. Imagine trying to write a detailed biography of a person who is 4.6 billion years old. You cannot just write one long, continuous chapter. You need to break their life down into major volumes and chapters to make sense of it all. That is exactly what this scale does for Earth. It is the official calendar of our planet, and understanding it is absolutely crucial for studying evolutionary biology. Now that we know what the scale is conceptually, let us look at why it is so fundamental. The geological timescale is a standardized system that relates rock layers, or strata, to specific time periods. Why does this matter? Because without it, scientists globally would have no way to correlate the fossils they find. It organizes massive evolutionary milestones, like the rise of dinosaurs or the sudden appearance of new life forms. It provides the essential framework we need to understand the rate at which evolution occurs over millions of years. Understanding this grand timeline requires a structured hierarchy. The scale is divided into nested categories, much like years, months, and weeks, but on a massive scale. Eons are the largest intervals. These are subdivided into eras, then periods, epochs, and finally, ages. For instance, we currently live in the Phanerozoic eon and the Holocene epoch. These boundaries are not chosen randomly. They are strictly defined by major events in the fossil record, such as the 5 major mass extinctions, showing us just how fragile existence can be. So we have this hierarchical calendar, but how do we actually assign specific numbers, like 66 million years ago, to these boundaries? This brings us to radiometric dating. When a rock forms, it contains unstable parent isotopes that slowly decay into stable daughter isotopes. Because this radioactive decay happens at a constant, predictable rate, it acts like an internal clock. By measuring the ratio of parent to daughter isotopes in a rock today, geochronologists can calculate exactly how long ago that rock formed, giving our scale its precise numerical ages. This concept of radioactive decay gives us a highly practical mathematical tool. This is the age equation, used directly by scientists to solve for time. Let us break down the symbols. The variable t is the age of the rock we want to find. The symbol lambda is the decay constant, which is unique for every radioactive element. N0 represents the initial number of parent isotopes, and N of t is the amount remaining today. The natural logarithm function reverses the exponential decay process. When the remaining isotope is very small, the logarithm yields a larger number, meaning the rock is much older. Before we move on, let us see this formula in action with a concrete example. Suppose paleontologists find volcanic ash right above dinosaur fossils, marking the famous KT extinction boundary. We are given a decay constant of 1.05 times 10 to the negative 8 per year, and mass spectrometry shows the isotope ratio is exactly 2.0. We plug these values into our age equation. The natural log of 2 is approximately 0.693, which represents the half-life relationship. Dividing this by the decay constant gives us approximately 66 million years. This exact numerical value anchors the extinction of the non-avian dinosaurs. Now that we have successfully used the age equation, let us understand where it actually comes from. We start with the fundamental equation of radioactive decay, which states that the remaining isotopes, N of t, equals the initial isotopes, N0, multiplied by e raised to the power of negative lambda times t. Here, E is the base of the natural logarithm, approximately 2.718. To isolate time, our first mathematical step is to divide both sides by n0. This gives us the ratio of remaining to initial isotopes on the left side. Continuing our derivation, we need to bring the time variable down from the exponent. We do this by taking the natural logarithm of both sides, which mathematically reverses the exponential function. This leaves us with negative lambda times t on the right. Next, we use a property of logarithms. Inverting the fraction inside the log flips the sign, giving us negative natural log of n0 over n of t. Finally, we divide both sides by negative lambda. The negatives cancel out, and we arrive at our final practical formula for time. This is the exact equation we used to date the dinosaur extinction. This mathematical foundation leads us to another important calculation. To truly grasp the immense scale of geological time, we often calculate what percentage of Earth's total history a specific period represents. The formula is a simple ratio. We take the duration of the specific period, divide it by the total age of the Earth, and multiply by 100 to get a percentage. The physical meaning here is profound. It helps us visualize just how long the planet existed before certain evolutionary milestones occurred. Remember, you must always ensure both time values are in the exact same units before dividing. Let us apply this percentage formula to a real evolutionary question. The Phanerozoic eon, characterized by abundant, complex animal life, began about 541 million years ago. Earth itself is 4.6 billion years old. First, we convert Earth's age to 4,600 million years, so our units match. We place 541 in the numerator and 4,600 in the denominator. The units cancel out. Multiplying the decimal by 100 gives us 11.76%. This means for nearly 90% of Earth's existence, life was restricted to microscopic or very simple organisms. To visually reinforce what we just calculated, let us look at the geological time clock. This diagram compresses Earth's entire 4.6 billion year history into a single 24-hour day. Notice how the Hadean, Archean, and Proterozoic eons take up almost the entire clock face, from midnight all the way until about 9 p.m. This vast region represents the time of single-celled and simple life. That tiny slice at the end, the Phanerozoic eon, contains the Paleozoic, Mesozoic, and Cenozoic eras. All the diverse, complex life we see in the fossil record, including dinosaurs and humans, is crammed into just those last few hours. We have covered a massive amount of time today, so let us summarize our key takeaways. First, the geological timescale is the foundational framework of evolutionary biology, acting as Earth's standardized historical calendar. Second, we learned that this time is organized hierarchically, from massive eons down to specific ages. Third, through the mathematics of radiometric dating, we can assign precise numerical ages to rock layers by measuring radioactive decay. Finally, our calculations revealed the breathtaking immensity of deep time, showing that complex life is a relatively recent chapter in our planet's long, dynamic story. Excellent work today.